Good afternoon. Welcome to Purdue University and the CERIAS Security Seminar. Our speaker today is Professor Chip Killian, first-year assistant professor here in the Purdue Computer Science Department, recent grad from University of California, San Diego. His talk today is titled Mace, Systems and Language Support for Building Correct, High-Performance Networked Services. Chip?
Thanks. So my research is, as he said, it's on how do you build correct high-performance distributed or networked services, and so where I sort of meet security in this line is trying to keep bugs from getting into the code in the first place so that people have nothing to exploit. So when I talk about a distributed system, right, this is a fairly heavily used term, so we'll first talk about what I mean when I say that. I actually have a very broad class of system in mind when I talk about a distributed system. So this includes things like the stock exchange, where you have computers talking to other computers, executing buy and sell transactions in order to keep the market going. And this is going to be a distributed system. Then there's a commuter train system, where you have a distributed system which is monitoring where all the various trains are, as well as making sure they don't collide with each other, routing them on the different tracks, keeping them in line. So there's a distributed system which is monitoring this. I'm also talking about things like the telephone network. Right? There's a very complicated set of telephone long-distance switches which interconnect the telephones all over the world, and when you make a phone call, we're routing communications from one telephone to another telephone through a distributed system. This will also include air traffic control centers. Right? Airplanes transmit requests to the air traffic control centers, who will route the planes through the airspace to make sure they don't collide with each other, send the route requests back to the plane so that they can then fly. That's a distributed system because you have data which is starting in one place, it's being shared with other places, other computers elsewhere, and they're working together to accomplish a goal. This will also include trauma centers. More and more these days, trauma centers are also being run by distributed systems. So, for example, they'll install a main computer which has the job of farming out tasks to subcomputers to execute diagnostic tests. So the doctor comes in, they ask for some diagnostic to be performed, it gets farmed out to some subsidiary computer, which gets the result back to the doctor. Again, this is going to be a distributed system. And then finally, everybody's favorite voice over IP protocol, Skype. Many of you have probably used this to talk to friends around the country, around the world. This is actually a peer-to-peer type of distributed system where nodes will communicate through other third-party nodes in order to establish computer-based phone calls. So this is also a very big class of distributed system. I think this one has lots and lots of users. But these aren't all just distributed systems. These are, of course, all examples of flawed distributed systems, or systems which have failed, sort of in many cases, quite gloriously. And when I say gloriously, I mean they make the news, and they make the news in a big way. Right? When the stock market has a problem, it's a big news item. So in this case here, the computers which were monitoring and maintaining the Dow Jones Industrial Average were, due to a software bug, having trouble keeping up with the average. And it happened to be a poor trading day, which meant the average was going down, but the computers weren't keeping up with it. And so it looked like a fairly slow decline throughout the day. Eventually, someone discovered that there was a problem, and they failed over to the secondary computer for monitoring the average. It quickly brought the average up to date, which brought the system back into sort of an equilibrium. But the unfortunate part is that this meant that as far as the investors could see, the average, which started out pretty good, declined slowly, spiked downward several hundred points in a period of about 2 or 3 minutes. This made the investors very unhappy, and they increased their sells, which caused the market to go down even further. So when distributed systems fail in this way, it's not just annoying, it's actually expensive. People lose a lot of money when this kind of thing happens. Then there was a malfunction in San Francisco where a network operator disconnected the connection between the trains and the central routing station as he was preparing to transfer to a new switching station. And so as a result, the central train system couldn't figure out what to do, and so the trains all fell back to their fail-safe mode, which is sit still on the tracks. So there were no train collisions, but for a period of about 30 minutes during rush hour traffic in San Francisco, there were 8 trains worth of people stuck on the tracks, couldn't get to work. So again, time is money, and this is a big deal. Then there was a glorious outage of AT&T's long-distance switches in 1990. Whenever the long-distance switch received a particular signal, the long-distance switch would reboot. In and of itself, that's a fairly benign type of failure. The problem is that when the switch rebooted, it would send this same particular signal to all of its neighboring long-distance switches, causing them to reboot. And of course, this provided a very cascading failure, which left large portions of the country without long-distance service for a period of many hours before they were able to roll it back to a prior firmware version. There's plenty of cases where distributed systems aren't properly configured for the load they might expect. In the lower case here, the FAA took down the Atlanta Center for Routing Flights and redirected all the traffic to Salt Lake City, which couldn't handle the load, causing hundreds of cancellations and delays of flights. And in the top case, the LA County's main hospital brought online a new central computer. This central computer, this new one, couldn't handle the load, and so the hospital became unable to perform diagnostic tests until they got the old system back online. This meant that doctors couldn't get results. They had to diagnose patients by just looking at them, and they had to reroute ambulances from the LA County main hospital to other hospitals in the area. And then, of course, in 2007, Skype had an outage when a major nameless software operating system provider released on a certain Tuesday of every month a set of software patch updates, which this software company's users all downloaded and ran at the same time. And then they rebooted their computer. This caused a very large churn of users of the Skype system. And the protocol was not designed to handle such a sudden, large change in the number of people. And so the joining protocol, which requires them to communicate with a certain set of established peers, was unable to complete. And so Skype had many millions of users who couldn't talk on the phone for, I think it went on for a couple of days before they were able to get the protocol fixed. So these are problems that do occur in distributed systems and deployed distributed systems. Some of them might have been preventable. Others of them, some of them are hard to prevent. Some of them, you could have prevented fairly easily. But what we want to do is we want to draw attention to these kinds of problems so that we can look towards building new systems with new tools that will help us to avoid these problems in the first place. So, in order to do so, I need to introduce you to the canonical distributed systems developer circa last year, and that's Fred Flintstone. Fred Flintstone is our favorite Stone Age distributed systems developer. He's been at his job for a very long time. He has a lot of practice and experience in building distributed systems, and he's gotten quite good at it over the years through hard work and practice. So let's talk about how it is that Fred builds a distributed system. So first, he has to choose a programming language for his distributed system. And using these technologies, he essentially has to choose between a programming language that gives him good performance or a programming language that makes it easy for him to build his distributed system. Now, Fred, being overly concerned with the performance of his distributed system, is going to pick a fairly low-level implementation language like C++, which will lead him to an unstructured implementation. And by unstructured, I mean that the code is sort of haphazardly placed in a wide variety of files in the source code directory, and there's sort of no rhyme or reason to how it's put together, making it hard to understand. He then takes this implementation and he takes it over to a small LAN where he does some testing. And because he's a good coder, with a few small tweaks, he's able to get this implementation to work. So he's happy, right? He takes this implementation, it's now a working implementation, and he takes it to the internet, ready to run it on the internet. But when he runs it on the internet, he finds that sometimes it works, but occasionally it fails, and oftentimes it's slow. And so now he has to debug this distributed system, which works on the LAN, but not on the internet. Now, in order to do that, he's going to use the state-of-the-art debugging techniques for distributed systems. Namely, he's going to stick printfs in his code. Right? For distributed systems, this is basically as good as it gets. So, when he adds printfs, right, he can't reproduce it on the LAN because the LAN is not a large enough scale to exhibit the problem. But when he's added this logging, he can't reproduce the problem on the internet because the logging has added too much overhead. So he faces this problem where he can't debug the system adequately on the internet, he can't debug the system adequately on a LAN, and so he needs some other techniques. Currently, what Fred does is he continues to deploy it. He waits for users to report problems. He listens. He reasons about the reports that he gets, and he updates the code accordingly. So my research, Mace, that is to bring in a new era of distributed systems programming. So we take Fred, who uses